So the first part of this presentation shows how Vibro-Acoustic method is used as a fast diagnostic tool to easily detect mechanical problems in the tap changers online or offline before they create an outage. So the second part will present a real case showing how New Brunswick Power has used this tool to adjust properly an OLTC. So 40 to 50% of the failures on transformers come from tap changers and are of mechanical origin. So 4 studies done by Hydro-Quebec, ESCOM, CAA, Australia during 10 years on 3 continents, confirmed by Seagray, IEEE show the same results. Here you have a graph where you can see that 45% of the failures come from the tap changers. What are the existing methods for OLTC testing? So we have 5 methods: the Vibro-Acoustic, the motor current, the dynamic resistance, the dissolved gas analysis, the thermography. And the Zensol is able to do these 3 tests in one instrument. And this is the kind of problems that you can find, that you can detect when you have linkage gears, timing sequence, control relays, motor, brake, lubrication, alignments, arcing, overheating, contactor, and transition. And here you have each method is good in one field. For example, the brake is very good for the motor drive testing. So here, the Vibro-Acoustic method offers the widest detection spectrum, and this table, it comes from Seagray 8034, and we have also a reference in Vibro-Acoustic monitoring recommended by IEEE. I recommend really to take some time and study these tables. It's really interesting because it gives like an overview of what which method is good in which the testing problem. So what kind of benefits OLTC's Vibro-Acoustic testing bring to electric utilities? First of all, it's applicable to any kind of tap changers. It's applicable online or offline. And it's a quick, easy, and intuitive test similar to a stethoscope. We have an advertising. Well, it's like a picture where you see transformer, a high voltage transformer coming in a vibro therapy room, and with a stethoscope, so the doctor is able to listen the high voltage transformers speaking or in fact vibrating. So with vibration and current combined, we're able to detect a large range of potential problems. This gives us a better understanding of how the tap changers work. And this part is important because each impact you have to understand why you have this impact. As soon as you do this effort, so it forces you to understand what kind of architecture, what kind of hardware you have in the tap changers. And this effort is very good to so thanks to this understanding, we can detect problems at earlier stage. And the method is excellent in terms of timing and mechanical adjustment. The next presentation, we will show how New Brunswick Power has used this tool for the timing and mechanical adjustment. It's also an easy tool to detect arcing and contact problems, online only, of course. We have a software, and thanks to Hydro-Quebec envelopes, we are able to detect a lot of problems. And we have a high sampling time, and with an unlimited recording time, which is unique in the market. And when it's a quick tool, so this tool helps the user to decide which OLTCs are due for a maintenance operation. And in testing OLTC before and after maintenance, this tool can also be used for quality control. And in testing year after year, trending analysis becomes easy and allows a reduction of maintenance interventions. And of course, our goal is to reduce the transformer failures. This you have a resistive OLTC type diverter switch operation sequence. For example, here we are in in tap 3, and we are moving to tap 4. And typically for the resistor OLTC type, the transition of the diverter switch is done in only 50 milliseconds to avoid overheating the resistance. So this value is important because it helps you to check if the vibration that you can see here is done in 50 milliseconds. So we are able to listen all the impacts of the mechanism during a step up or step down operation. And another parameter which is important also, it's the motor operates between 2 and 12 seconds. So with these two information, we must find these two informations in our Vibro-Acoustic signature. The motor drive mechanism. So this motor allows the tap changer to move from a position to another, and in recording, analyzing the EC or DC current of this motor during the step up or step down operation, we are able to know if the mechanism are forcing or not. And another information is that the motor current allows us also to start and stop the recording. So in fact, we just focus on the window of the operation. So the diagnostic principle, it's what? It's each operation of any on-load tap changer produces a specific vibroacoustic wave pattern, or we call this a signature or a fingerprint. And with a vibroacoustic sensor, so which is an accelerometer, we can record the signal the same way a stethoscope picks up a person's heartbeat. And a stable OLTC always shows consistent signatures. And any degradation of the OLTC induces change in the signature. So we use the Hydro-Quebec envelopes. This method has been patented in 2001. And here on the left, you can see the raw data in the blue, what we call the envelope, which is calculated thanks to the software and the specific proprietary algorithm from Hydro-Quebec. So we get here, you can see the envelope. And in fact, what we have the motor current envelope that you can see on the bottom here. And here, this is the high frequency envelope and the low frequency envelope. So the question is, why envelopes? In fact, it simplifies the signal, because when you compare like a vibroacoustic, which is complex and a lot of informations, so it helps us to simplify the signal. We get the shape of the signal exactly like the human eye is able to see, like this raw data, we can see an envelope which is like the shape. And we can focus this way on valuable impacts only, and after it's easy to analyze and easy to compare. So impact understanding thanks to the envelope. So here you can see the motor current envelope, and in red, like for example, you have the impact of the diverter switch here, the selector switch, which is silent, diverter switch again, and here this is the breaking part that you can see here. So when we are able to understand on these kind of curves, so at this time you are sure that you understand exactly what is happening in your tap changer. So this part is sometimes it takes time, but it's a good effort to do. And this is, we have like a software, and here typically we have the raw data. Here you can see an AC current with a vibration that we record. And a diagnosis can be made in 15 minutes for an online test and 1 hour for an offline test. So here, this is the on-site quick analysis. So thanks to the envelope, we are able to see quickly if the tap changer is working properly or not. We have some Excel reports, and in blue, dark blue here, we see there is something maybe that you have to be careful with. And offsite deep analysis. So thanks to what we call the Excel report, which focus on the transition time, the amplitude of the envelopes, we are able to detect contact wear. We analyze the envelope. We have diagnostic cards, and we're able to compare with our Zensol database on OLTC reference signatures. Here we have an example of wear contacts. This is done in Val-Thietro, Hydro-Québec on an EBB UZ ERN. Here we have, you can see like the contacts is severe wear of contacts. And here you have a superimposition of high frequency and low frequency envelope. And before the intervention, more than 60% of difference between the high and low frequency. So this like an alarm that something is maybe wrong inside. And effectively, this what you can see here. And after the repair, after the intervention, less than 20% of difference between the high and low frequencies, as you can see here. Here it's already a simple problem, very easy to detect. Here you can see that the motor current is forcing here. And because usually this curve is absolutely flat. When the motor current, the motor drive works properly, you have a flat plate. Also, these problems are easy to detect. The example of asynchronism, as you can see here, before repair, you can see that the switching appears 120 milliseconds after the end of the current. So this is not normal. And after repair, when it was just to uncouple the motor drive and to change with another, like, I don't know the word, I'm sorry, to uncouple it and put it in a new position, and this has solved the problem after repair. An example of arcing contact. Here you have a comparison between online and offline test. On red, it's 7G, it's offline. On black, it's online. And when we zoom these two parts, you can see here, like on the red, it's the offline, and the arcing happens at this position of the contacts. So this gives you a good indication of what is happening inside the tap changer. Here what we try to do is always to do impacts and timing association. These curves and this how do you say, this picture is given by the manufacturer, and what we do, we take the impact, the Vibro-Acoustic envelope, and then we do an association of on which position of the transition. Here it's also the simple example of abnormal in rush current. Here we have a comparison of the inrush currents between two transformers, same type, and the one on the green one was producing like a breaker was putting in fault because it was not, the tap changer was not working properly. So here you can see it's easy to detect and see with the motor current. Here it's another example of the forcing current. So there is something to do for the motor current in this curve. And break analysis also. With the break analysis, we have some click that happens just after the end, and so it shows you that you have to be careful about it. So the challenge is how to facilitate the compression of vibro-acoustic signature, and several mechanisms are operating at the same time. So one way to address this challenge is to analyze simultaneously three recordings: the vibration, the dynamic resistance, and the motor current of the tap changer in action. So the equipment needed here, you have what we call the tap 4+ on the bottom, and the tap DRM, which is an accessory which injects current on the tap changers, and of course the transformer must be offline. Here you see the kind of installation that we do. And example of DRM recording, I'm not going to talk about this curve because it's well known for the DRM curves in the industry. And here you can see here with the high-speed camera the tap changer moving. And in fact, we do at the same time the Vibro-Acoustic and the DRM. So here we have this is the first step. The second step, when the transition is put in parallel, when the resistance is put in parallel, same here. And then we get, and finally we get this, the dynamic resistance. And so it's easy after to put in relation the transitions, real, and the mechanical impacts that occurs when the transition happens. And on the bottom, this is the motor current. So here we have exactly the same with a high-speed camera. So you can see on at what time you have the impact and what is the resistance transition. These are examples of recording for different OLTCs done with tap 4+ and the accessory tap DRM for an MR or an EBB. So this is what we recommend: an example of action plan to elaborate a predictive maintenance for transformers with OLTC. Step 1, it's establish your transformers list with the OLTC to monitor. Step 2, for each transformer, do a complete test to get a reference, all taps offline, tap 4+ and tap DRM, and we have developed a Zensol checklist. Step 3, we produce a complete report analysis for each tap changer with the transformer. So we have a Zensol, we have developed also Zensol template report analysis. Step 4, according to diagnosis results, you can establish your maintenance plan for each transformer, because at this time you have a lot of information on your tap changers and your transformers, if they work properly or not. Because in this effort, when you're able to do really the step 3 properly, you have exactly, you know exactly how your tap changers are operating and if they work correctly or not. And the step 5, so after you can do a vibroacoustic test online or offline only without the DRM. The DRM has been used just to help you to understand the vibroacoustic and when the impact is occurring at the time of the transition of the tap. So here, this is the second presentation. In fact, this presentation has been done by Christian Noel, which is a professional engineer in New Brunswick Power, and has been presented the first time in the SANC 2023 in Fredericton. So me, I'm just like the presenter of this PowerPoint. So the test has been done in Caracat. The name of transformer was T1. It was a LTC maintenance, MR type, M3D500, and the vibroacoustic and DRM performed before and after maintenance. And this maintenance was performed on the Caracat T1 transformer, and this transformer is equipped with a Renhausen type M3 Delta 500 tap changer. So please do not ask me detailed questions on this kind of tap changer. So here, the LTC type. So in general, there are 2 types of LTC, compartment or box type and in-tank design. In our case, this LTC is an in-tank design, and although most of our in-tank design LTCs are 3 separate phase models, we do have a few delta configuration, and the delta configuration has a cylinder with 2 diverters, as you can see here on the right, and the other is a regular cylinder with a single diverter. Here, the timing between the motor drives and diverter assemblies is adjusted using the shaft connections between them. So here you have these are connected here. So vibroacoustic sensors, sensor location. In this case, we installed 2 vibroacoustic sensors, 2 on separate walls near the diverters, and located about 18 inches from the cover, as you can see here. So this is the vibroacoustic measurement. Generally, tap operation on this style of tap changer will include the following steps. One of the selector contact is leaving the previous tap position, stationary contact. This moving selector contact is then connecting to the next tap stationary contact, and the energy in the diverter energy accumulator is released to switch the load current to the next tap connection. On this graph, we are seeing the sound made by each operations being captured by both vibroacoustic sensors and also the MDU motor current captured by the EC clamp on CT. This is the motor current, and here the accelerometer 1 and accelerometer 2. And in fact, we need only 1, but in this case, they have preferred to use 2. So when adding the DRM information to the previous graph, we can then confirm when exactly the diverters are switching the current. It helps understand the information provided by the vibroacoustic sensors. For example, here, if we don't have the DRM information, you will have here 3 impacts, and your like normal question is what means this impact, what this one means, and what the other one means. In fact, with the DRM, we know that we have to focus on these impacts only, not the others. So tap up operation before maintenance. The results shown are from before the maintenance. We've seen all 3 phases side by side. So phase A, B, and C. From this information, we can tell that A phase is not operating in synchronization with B and C phase. A phase is likely the single diverter, where B phases are associated with the double diverter cylinder. So here, I would like you to notice the DRM here and these impact. This is for B, and this is for C. And when you see the A in comparison, that you can see the transition is happening on this impact. So there is something which is not correct. So before maintenance, our test plan calls for testing all the tap transition going up and also back down. In this up operation, we're seeing the A phase is operating early than B and C that you can see here. So, but in the down operation, we are not only saying that A phase is operating slightly later than the other two phases. In fact, A phase is operating after the motor current is interrupted. This is what you can see here. The motor current happens here at the end, and the transition is happening after the motor current. So the timing of this diverter is at the limit where it could possibly not operate during a down operation. This would result in a phase being on a different tap when the other two phases. Here, tap up after maintenance. This graph is now showing the acoustic signatures and DRM information recorded after our maintenance. We're seeing A phase operating now around the same time as B and C phase originally, about 4.25 seconds. So you see now we're not in this impact, we're here. Tap down, but the big improvement can be seen on the down operation where A phase is operating well within the runtime of the motor now. So like in the previous, this was happening at the end of the motor current, and now this aligns with what was seen for B and C phases. So for the tap up, the before maintenance, just to review the before maintenance reading, showing the difference in timing between A phase and the other two phases that you can see here. And after maintenance, the after maintenance results now indicate the timing between all three phases is now better adjusted, and the selectors and diverter operations are now more in synchronization. I'm not showing the down operation, but the timing was the same as the up operation shown on this slide. So Zensol Tap 4 can give a good indication of the timing between diverters. When time allows it, it can be used before and after maintenance to validate the LTC is operating properly after our intervention. As we're gaining more experience with the information provided by the Tap 4, we could use offline acoustic measurement to focus prioritize maintenance on specific units. So Randy, I think I have finished. So
great. I have a few questions here. You mentioned that 40 to 50% of transformer failures are caused by tap changer failures. Why is this? And what kind of mechanical failures are there that cause this high rate?
Well, in fact, it's a study, as I said in the second slide, I think. The study has been done by Sigri, Hydro-Quebec, and it's mechanical problems. I suspect personally it's because the tap changer is a complex mechanism. So as soon as you have something which is complex, of course, it's more sensitive to problems. So the design of the tap changers are complex. So this is like normal ones.
Okay.
Well, in my point of view, all the electric part, for example, when you have it in a transformers, you have a copper, you have a simple wires, and the kind of so as soon as you have a mechanical, you have motor drives, you have a complex mechanism. In my point of view, it's like a direct link to the amount of failures.
Okay. What is the relationship between vibration, dynamic resistance, and motor current?
What look in the past, in 2008, 2009, we have started just with the vibroacoustic and the motor current. The motor current, as I said in the beginning of the presentation, is it helps us to start and record and stop the recording. And the second, it gives good information on the motor current, if it works properly or not, just in measuring the current. If it forces, so there is some problems. So this is the first. And the vibroacoustic, when it's I can compare the vibroacoustic to you are in your car. What you do, you listen, you have like what we call a normal noise, which is your standard, which is, so in fact, what you do every day, you learn and you know the noise of your engines in your car. So this is your reference, this is your signature, this is your the normal sound. And one day this sound change, the noise changes. So at this time you say, hey, there is something wrong. If you get like an impact on the front right wheel, you will listen it. And the vibroacoustic is doing exactly the same. We record the vibration of the tap changer when the operation happens. And the problem, in fact, we have some impacts, but it's hard to do when this happened because there is a transition. Then and the DRM helps us to identify which impact is occurring during the transition of the tap changer. So it really helps us to learn the vibroacoustic signal. And
Okay.
with three signals, so it's important to have them in parallel, because as New Brunswick Power has done, it's thanks to the DRM, the vibroacoustic, and the motor current that he was able to see that was something wrong. The current gives you the end of the transition, but the impact was not happening. So this is not normal, because you are not sure that it's if your if your motion is finished or not. So it could be dangerous, and sometimes the tap could explode. Well,
Okay. I have another question. Is there an advantage to tapping the transformer windings at the three levels, high, mid, and low, as opposed to all legs being tapped in the middle?
What? So in fact, what I understand of your questions, so you want to have just like one tap. So for example, you have a 33 taps, and you put your tap in the middle, right? We do not.
Well, that's the question. Peter Nichols asked that question. Is there an advantage to tapping the transformer windings at the three levels, high, medium, and low, as opposed to all legs being tapped in the middle? I guess having the three levels tapped separately as opposed to having them all tapped in the middle.
Well, what I can answer, well, I don't understand very well the question, but what I can just describe what we do. We do all the taps just to be sure if all the taps are working correctly or not, because a lot of times some taps are not working, like for example the first ones, because usually the transformer works on like in some position and then do not move a lot if there are no variation in the voltage. And we go through all the taps when we are offline, and online we just work on 2 taps up or 2 taps down. And also for the DRM we do 3 phases separately. We do not personally we work always, we try to work separately on each phase. And also we try to do all the taps. And because, well, doing working differently, I'm not sure it will be a good idea.
Okay, that's great. That's a good answer. Peter, I hope that answered your question. Okay, there's no more questions. Fouad, thank you very much for another excellent presentation.